Hello everyone, in this lesson we will discuss Layer 2 and Layer 3 forwarding issues and VLAN issues, Cisco Express Forwarding, that is, CEF in our next lesson. Now let's talk about Layer 2 forwarding first. The data link layer, which is the second layer of the Layer 2 forwarding OSI model, manages addressing below the IP protocol stack, so that communication between hosts is routed. In Layer 2 MAC addresses are used for communication. Now let's look at the term collision domain. The Ethernet protocol first used technologies such as ThinNet and ThickNet, which connected all network devices on the same cable and using T-connectors. Communication was disrupted because all devices shared the same segment and cable. Ethernet devices use carrier-sense multiple access collision detect to ensure the communication of only one device at a time in a collision domain, which means that devices can only transmit and receive data at a time, meaning that our devices can work half-duplex. The hub devices used in the past also replicated this problem because the hub devices are not smart devices. All the active ports they diverted traffic to all ports. On switches, virtual channels are created to increase scalability and stability in a network. Using the MAC address table instead of moving all traffic through a switch port, forwarding network traffic only to the port of the target switch to which the destination MAC is attached. This greatly reduces the size of the collision area between the devices and allows the devices to send and receive data at the same time, meaning that the switches can work as full duplex, the hubs work as half duplex, but the switches can provide bidirectional traffic. In the figure here, the collision domain example of the hub device and the switch device, the hub device transmits the package to all the users here, so all the users here are all in the same collision domain, but when we look at the switch here, if there are 3 users, there are separate collision domains among the 3 users, so when the PCA user here will send the package to PCB, the target MAC address is on the switch, which port is on the port, but the hub does not have such an option. When the PC sends the A package, it forwards the packet to all the active ports, but the switches do not work that way. But what happens if a packet is sent to an address that is not in the MAC address table? The switch will then forward this packet to all ports. In this we call it unknown unicast floating, since the destination MAC address is unknown. Broadcast traffic is the network traffic sent to each host on the network and is forwarded to all active ports. This traffic is annoying because it can cause communication between network devices to stop due to carrier-sense multiple access collision detect. Broadcast traffic does not pass from one subnet to another, assuming all devices in the same Layer 2 segment are in the same broadcast domain. The figure here shows unicast and broadcast traffic, where unicast traffic goes from PCA to PCB, and when PCA sends traffic from here as unicast here, the traffic goes to PCB. In the case of broadcast traffic here, if the PC does not know the destination point to which it will send the traffic, it broadcasts a broadcast packet to the network here, and this broadcast packet is transmitted to all active ports on the switches. On this page, let's talk about VLANs. We examined VLANs in detail in our CCNA training. In this lesson we will make a reminder for VLANs and I will talk about native and allow VLANs. Adding a router between networks helps to shrink a broadcast domain and ensures optimal networking, which can lead to inefficient use of hardware as more ports are needed. VLANs provide logical partitioning by creating multiple broadcast domains on the switch if they are the same. VLANs provide higher utilization of the switch's ports because they can be associated with one broadcast domain and multiple broadcast domains can be used over the same switch, while network devices in one VLAN cannot communicate with devices in a different VLAN through Layer 2 broadcast traffic. The package header of the VLANs is also as shown in the figure here. The 12-bit part uses a VLAN ID and specifies our VLAN number, where the TP-ID is set to 16-bit space 0x8100 to identify a package as an 802.1q packet, and this 3-bit field is the field that allows us to specify QoS settings as part of the quality of service between switches. The drop eligible indicator section here is the area that shows whether to drop packets when there is bandwidth contention. Since the VLAN ID is only 12 bits, we can only use 4094 VLANs. Let's take a look at these VLANs that we can use. VLAN 0 is reserved for 802.1p traffic and cannot be modified, cannot be deleted. VLAN 1 is the default VLAN on switches, which cannot be changed or deleted. Our VLANs from VLAN 2 to 1001 are normal VLANs we can add, change or delete if necessary. VLAN 1002 to 1005 reserved cannot be deleted and changed. We can use them as extended VLANs in those from 1006 to 4094. I also wrote here how you can configure VLANs, which you have already learned in CCNA training. On this page, let's talk a little about access ports and trunk ports, and then let's continue our lesson by talking about native and allow VLAN. Access ports are the basic building blocks of a managed switch. An access port is assigned to only one VLAN. Traffic is moved to other devices connected to it on the specified VLAN or located in the same VLAN on that switch. 801.q tags are not included in packets transmitted or received by the access port, which means that 802.1q packets are transmitted on trunk ports. Now let's talk about the trunk port briefly. Trunk ports are usually used when we need a connection between one switch and another switch, router or firewall of multiple VLANs. When a packet is received on the trunk port, the packet headers are examined, the traffic is associated with the appropriate VLAN, and then the 802.1q headers are removed and the traffic is forwarded to the destination port on that VLAN. Now let me briefly talk about native VLAN. All traffic advertised or received on a native VLAN port without 802.1q VLAN tag is associated with native by default. The default is VLAN1 on native VLAN switches. If you change native VLAN in one switch, you need to change native VLAN on other switches as well. So you need to specify the native VLAN under the trunk port here, and you need to specify the native VLAN in the switch here. For example, let's say you connected a hub to port 10 of the switch. Let's say you connected the hub. Let's say the port is VLAN 50. Here under the trunk you need to specify native 50. In the same way, you need to specify that the native VLAN is 50. 802.1q trunking protocol tags are not added to packets transmitted in native VLAN. Let's talk about allow VLAN. With allow VLAN we can determine the VLANs that will pass through the trunk port between the two switches. VLANs other than those VLANs that are allowed, VLANs 1, 5, 10, 20, and 99 in the example configuration here, do not pass through the trunk port here. If you say 1-5 it covers from 1 to 5. If you want to specify specific VLANs you need to put a comma between them as shown here. You can write 10, 20, 99. We use the allow VLAN command to allow VLANs to pass through the trunk port in this way. On this page, let's talk about Layer 3 forwarding. We have looked at how Layer 2 traffic has been transmitted so far, and now let's review the process of forwarding the package from the perspective of Layer 3. If we remember that all traffic starts at Layer 7 and moves towards Layer 1, we will remember that some of the logic of Layer 3 forwarding occurs before Layer 2. There are two main methods for Layer 3 forwarding. The first method is to route traffic to a device in the same subnet, and the second method is to route traffic to devices in a different subnet. First, let's look at local network forwarding, and then we look at the routing between different subnets. Two devices in the same subnet communicate locally. Because the data is encapsulated by IP address, the device detects that the target is on the same network, but the device needs to place the source and MAC address information in the packet. It knows its own MAC address but does not initially know the MAC address of the target, for which ARP is used. Let's remember what ARP was for. ARP was a protocol used to store the IP address of a device and its corresponding MAC address, and Layer 3 was used to match IP addresses to Layer 2 MAC addresses. The device uses the ARP table before sending the data packet to Layer 2, which maintains records in the ARP table of devices in the same IP network segment that have recently communicated. Now let's look at packet routing on this page. When two devices are on different networks, packets need to be routed. Because the data is encapsulated with their own IP addresses, a device knows that the destination is on a different network and needs to be routed. The device checks the local routing table to determine the next hop IP address, can learn the destination network, subnet mask, and next hop IP address from a static route entry in the local routing table. The default gateway is also a static route that defaults to the local next hop, which is learned from the routing protocols in the routes. The figure here shows how the packet is transmitted. The PCA user here needs to send the packet to the source IP address 192.168.1.1, 192.168.2.2, so he needs to send it to the user here. First, it needs to forward the packet to its default gateway, where it adds its source MAC address, and since it will forward the packet to its default router, it forwards the default router MAC address to the default router. The default router receives the packet, checks the destination IP address in the packet in the routing table. If it knows the route to subnet 192.168.2.0 in the routing table, it takes the packet and changes the MAC addresses here, adds its MAC address here, and sends the packet by writing the MAC address of the port to which it will forward the packet in the destination section. On this page, let's briefly talk about forwarding architectures. Routers first receive a packet and first remove the Layer 2 information and check if the route exists for the destination IP address. If it cannot find a matching route, it will drop the packet. If there is a matching route, it will send the packet. IP packet swapping or IP packet forwarding is a faster process for an input interface to also receive a packet and decide whether to route or drop the packet to an output interface. This process has been simplified so that a router can forward a large number of packets. When the first Cisco routers were developed, a mechanism called switching to switching was used to exchange packets through routers, but today fast switching and Cisco Express forwarding have been created to optimize the switching to switching process so that Cisco routers can handle larger packet volumes. Let's talk about process switching on this page, and after explaining this subject, we will complete our lesson, and in our next lesson, we will deal with the CEF topic. Process switching is a switching mechanism in which the general-purpose CPU in a router is responsible for packet switching, while in iOS, the IP input process is run on the general-purpose CPU to process incoming IP packets. Process switching is required for source and destination packets routed to the router, except that it is used in packets that require additional unknown information. For example, process switching is also used in processes such as ARP. In this way, it shows how process switching is used. The IP packet comes here, but it cannot be switched with Cisco Express forwarding, so the packet is sent to the CPU, and the packet is sent from there by looking at the information from the routing table and ARP table on the CPU. This is the topic I'm going to talk about in this lesson in a nutshell, so goodbye to see you in our next lesson.